Hey, it's Dr. J. Good morning. Today we're going to do polar graphs. As I was promising yesterday, the continuation of the polar coordinate system. I want to start off with just an ordinary rectangular grid. In my first example, how to graph polar coordinates using rectangular graph paper, referred to as a grid. So I'll do a few examples here. Let's start with, how about the polar coordinate 4 and pi. So we have a rectangular grid here. And so we have the radius is 4, the angle theta is pi. I remember pi is the same as 180 degrees. So starting here at the polar axis, we go out radius 4. And then we do an angle counterclockwise of 180 degrees. And that puts you right here, 4 and pi. Notice in rectangular coordinates, that point would be -4 and 0 in rectangular coordinates. But in polar coordinates, it's 4 and pi. Let's try another one. How about 5 and 2 pi over 3. So this time the radius is 5 and the angle theta is 2 pi over 3. That's 120 degrees. Remember, 1 pi over 3 is 60 degrees. So 2 pi over 3 would be 120 degrees. So we'd go out to radius 5. Now, the y-axis, that's 90 degrees. Okay. Now, you might want to be a little bit more precise this time. In my first example, I just rotated exactly 180 degrees because that's easy to do. Any multiple of 90, 90, 180, 270, or 360, you can easily identify just freehand. For this one, I wouldn't do it freehand. I would actually convert so that you can find the x and y coordinates. So x is r cosine theta, y is r sine theta. So x is 5 cosine 2 pi over 3. So that'll be negative 2.5. Not sure if you can see that. No, you can't. Let's see. Let me just draw it a little bit higher. X is 5 cosine 2 pi over 3. And y is 5 sine 2 pi over 3. You can see that a little better. So x is 5 times -1/2. So -2.5. And y is 5 times radical 3 over 2. If you don't have your special angles memorized, you can use your calculator if it becomes necessary. But in this case, I think I'll just do a calculator to get a decimal. So I've got 5 times the square root of 3 divided by 2. So y would be 4.33, or 4.3 would probably be close enough. The x is actually exact. The y is an approximation. So my radius is 5. My angle is 2 pi over 3. And so that puts me at negative 2.5 and positive 4.3. You can just estimate about about 4.5. You're not really going to be able to get 4.3. So this would be the coordinate 5, 2 pi over 3. That's about 120 degrees, yeah. In fact, it's very close. It's probably like 119.5, or I mean, it's hard to be exact. As soon as you approximate, you're going to be close to 120 degrees. If I took out a little protractor and tried to measure that, I bet you'd be pretty close to 120. Yeah. Okay. Let's try negative 6 and 5 pi over 6. So remember, there's really no such thing as a negative radius, so you're going to go out to 6. Okay. Then you're going to do the angle of 5 pi over 6. 5 pi over 6 is about, well, it is, well, remember, 6 pi over 6 is the same as pi. So 5 pi over 6 is about 30 degrees, or is 30 degrees. So right about here. So here's my estimate, yeah. But then since the radius is negative, you want to reflect over here, yeah, negative radius. So you don't actually go here. You want to reflect about the origin. And so this will be your point. Now I want to be a little bit more precise. This is about where it will be. But I just want to be a little bit more precise. So we'll say negative 6 cosine 5 pi over 6. And that's for x. And then y is negative 6 sine 5 pi over 6. So you're going to get negative 6 times negative root 3 over 2. And negative 6 times 1/2. We might as well do the y. That's easy. Negative 3. So look. 1, 2, negative 3. My y value is exact. My x value is not going to be exact. I'm going to have to approximate it. It would be 3 root 3. That's about 5.1. So on my graph, I would go x is about 5.1 and y is negative 3. So to be a little bit more precise, I changed my spot. But it should be basically what I just said. It's a reflection of negative 6. So negative 6, and then you reflect it. And that's how you get the negative radius. So remember, the radius is still 6. Yeah. It's listed as a negative to indicate the reflection. I typically like to remove this. That's the ghost of where, this is where positive 6 and 5 pi over 6 would have been. Okay. So this is how you would adapt a polar coordinate onto a rectangular grid. Notice it's a little bit of a chore. That's one of the reasons why we have a special graph paper for polar, which we'll be using in just a moment. I want to do one more example with the rectangular, make you suffer through one more of these. So example 2, write the polar form of the graph shown. I'm using rectangular coordinates. And I'm going to make a graph. It's a circle of radius 7. 2, 3, 4. Actually, I changed my mind. My board's not big enough to go to 7. We'll go to 5. I bit off a little more than I could chew there. So we got 5, 5, negative 5, negative 5. I'm not using any tools, so pardon my funny looking circle, but that's a circle. So what's the polar form of this equation? We'll start with the rectangular form. X squared plus y squared equals 5 squared. You might need a little refresher on your equations of circles from maybe intermediate algebra or something like that. And now use the conversion formula. X is r cosine theta. Y is r sine theta. Substitute these guys in. And solve this for r. Remember, in polar equations, we typically, whenever possible, like to isolate the r, kind of like in basic algebra, you always tried to isolate the y. Typically, it's not like there's a law that says you have to do that. It's just a tradition to isolate the r. So I'm factoring out my r. I'm using a Pythagorean identity. Sine squared plus cosine squared equals 1. And so my answer is just r squared equals 25. Okay, and so we take the square root of both sides. R is 5. Don't worry about the plus or minus when you're taking the square root in this case. I guess there are two possibilities, but typically we insist that the radius be positive. Remember, if the radius is negative, you still plot the positive 5, and then you would just reflect it over to the other side. So it would actually make the same circle. It would just look funny. Yeah. So there you go. Very simple equation. So this is a circle centered at the origin. Or you could call it the pole if we were using a polar graph paper. Okay, so that's it. That's the polar form. Almost seems too simple, right? You can come back to your picture and see why it's so simple. Theta really doesn't matter. This is an equation in which theta can be any value. Yeah. So notice this point here, r is equal to 5. Yeah. Right here, r is still equal to 5. Right here, r is still equal to 5. Even when you get over here to the negatives, r is still equal to 5. So all the way around the circle, r is equal to 5. 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 So it's like a wheel where every point r is equal to 5. Even in the negatives, the radius is still considered 5. Not every circle is centered at the origin. Not every circle is centered at the origin. We often have circles that are centered somewhere else. Now, when we're using polar form, it's very common to have a circle that is tangent, sort of a reminiscent of the calculus concept that we'll be learning next semester. So the circle is tangent, in this case, to the y-axis. So look at this graph, and let's find the polar form of this equation. So this graph is what we call tangent to the y-axis. Yeah, it's the same word from sine, cosine, and tangent, but we're using the word tangent in a different form. We mean tangential, which means the circle is touching the y-axis at exactly one point. It's a different definition of the word tangent. Okay, so this time my center is 3, 0. And in order for it to be tangent, the radius is also 3. Otherwise, it would not actually touch the y-axis. Just to get the idea of how the equations work, I'm going to start off with equations that are at least either centered, or if they're not centered at the origin, then they're tangent to the axis, or to the origin in this case. Okay, so start off with your form, maybe from a beginning or intermediate, probably intermediate algebra when you learn this equation. Your h is 3, your k is 0. So you have x minus 3 squared plus y minus 0 squared equals the radius is r, which is 3 squared. Now, I found this interesting the first time I did this. You're actually going to substitute r as a number, and then in another step, you're going to put r back in as a variable. And that sometimes causes confusion. So sometimes you might use a capital R here just to indicate that that r and the r that we're going to use later, even though they both mean radius, I don't want you to get confused with which r am I talking about. So this is the original r. The other r is your independent r that's going to vary. It's a variable r. And I'll explain what I mean by that when I'm done with the problem here. Okay, so this r, capital R, is this r from the picture. Yeah, starting at 3, 0. When I switch to my polar form, let me move this out of my way here. When I switch to my polar form, I'm going to get x squared minus 6x plus 9 plus y squared equals 9. And I'm going to solve this equation Getting rid of the 9s. Now, I'm not really, I used the wrong word. I'm going to simplify this into polar form. Yeah. So I need to get rid of my x's and my y's and write them as r cosine theta and r sine theta. All right, so all of my x's become r cosine thetas, and all of my y's become r sine thetas. So this becomes r squared cosine squared minus 6r cosine theta plus r squared sine squared theta. You're going to group these guys together and use a Pythagorean identity. So I've got r squared cosine squared plus r squared sine squared. I'm just grouping these two guys together. Yeah. And then I'm going to put my negative 6 r cosine separately, and then put that equal to 0. Set that equal to 0 because I already canceled the 9s a long time ago. Pythagorean identity here, that's going to give us 1. So this is 1. So now I've got to factor out my r. I have a common factor of r here. So I could factor it out. The 1 is technically right here. It's 1r. Yeah. But I'm just going to say r. Now I'm going to divide both sides by r. And solve this. And we're done. So we solve this equation here, and we get r equals 6 cosine theta. You might wonder where the 6 is in the picture. The 6 is right here. Let me let you see all that work for a second there. So this equation, let me just write it here, r equals 6 cosine theta, represents this circle in polar form. And so that's the reason why I was mentioning the difference in r's. The original r was always equal to 3. That's because the original r was centered at the origin. It was not centered at the origin. It was centered at 3, 0. That's this capital R up here. Yeah. So all of these points have radius 3. Yeah, they all radius 3. R is 3, R is 3, R is 3. Yeah. That's in the rectangular version of the formula. But when you go to the polar form, in the polar form, the radius could be as large as 6. Yeah. So when theta is equal to 0 degrees, in polar form, everything starts at the pole. So you have to imagine your radius is going like this. It starts at the pole and goes out to 6. And then as theta changes, you have different radii. So the radius is not always going to be 6. Yeah. the radius is going to go like this. 6, and then here it's going to be 5 point something, and then 4, and then 4.3.9, and then 2.7, and it's going to go around. And the same thing down here, you're going to have these radii that are not always 6. 6 is the maximum radius. Yeah. So in general, a circle that is tangent to the y-axis is given by r equals a cosine theta. And you've got two possibilities. If a is greater than 0, then the circle looks like this, where a is positive. Yeah. And if a is less than 0, then your circle goes to the left side of the y-axis. It still has the same diameter, the same radius. The radius is a over 2. Yeah. I don't put negative a when I draw this graph. I just call this a because this symbol here tells me that a is already negative. Right? This is subtlety in algebraic symbolism, where if you say a is less than 0 and then you put the symbol negative a, that screws everything all up because a is already less than 0, so negative a would not be appropriate. It's just a. Okay. So here are your two possibilities. I'm sorry the circles don't look like twins. They should look like twins. These circles should be the same size. So I'm just being sloppy here. I think we should probably move on to the polar graph paper now. Yeah, I hope you're all understanding the pain that we suffer, feeling the pain that we suffer when we use rectangular grids to draw polar graphs. Yeah, so let's put this away and let's use some polar graph paper now. So graph the function r of theta equals four sine theta. And again, this is the function notation. So I actually would just rewrite this as just r equals 4 sine theta. You might wonder, why do we even use that notation? It's just to indicate that it is a function of theta. In other words, r depends on theta. That's how we read this. That's terrible. My red is dead. It's kind of important that you read it that way, because if you don't know theta, then it's very difficult to find r, right? So r is dependent upon theta. Got some polar graph paper here. Hopefully this will be legible. Now, we haven't really done these before, so what we're going to do is we're going to make a table. I mean, unless you already know the answer, you can just draw it very quickly. But we're going to make a table and plot all the points, or at least 4 points, 4, maybe 5 points. So we have some grid here. So this is a classic polar graph paper. I've got sectors of pi over, what does it look like? Pi over 3. So this is 30, 60, 90, 120, and so on. So this would be multiples of pi over 6. Let's start at 0. So that's theta. And then we'll figure out what r is. So if theta is 0, then r would be, where should I put it? Let's put it right here. R is 4 sine of 0, which is 4 times 0, so r is 0. So our first point is right here, radius 0. Now we'll do 30 degrees, pi over 6, or if you prefer, 30 degrees. By the way, 0 is also 0 degrees. It's the only radian that equals its degree measurement. So r is 4 sine of pi over 6. Sine of pi over 6 is a half. So r is 2. So on my grid, I'm going to go pi over 6. That's this angle here. And I'm going to go out 2 units right there. So each concentric circle represents 1 unit. So I went out 2 units. All right, let's go to 60 degrees, pi over 3. R is 4 sine of 60 degrees. So r is 4 times radical 3 over 2. So r is 2 radical 3. So that's about 3.5. It's 3.46 if you really want to be precise. I don't have a fine enough grid to do 3.46, so I'm going to do 3.5. So I'm going to go up here. I got pi over 3. That's 60 degrees. And I'm going to go out 3.5 units right about here. Right in the middle of the third and the fourth concentric circle. Next, we'll go to 90 degrees, pi over 2. So we're going to get r is, I know I'm a little bit off here on where these r's go. Let me kind of clean up my work here a little bit. So now I'm doing this one. That'll be 4 sine of pi over 2, which is 1. 4 times 1, so that's just going to be 4. All right, so pi over 2 is up here, 90 degrees. 1, 2, 3, 4 units. So notice what I have here. I have half a circle already. Yeah. I could probably just complete the circle and be done with it. Let's go ahead and just put it into my table to be clear about it. So I would do 2 pi over 3, and the y value would be 3.46 again. Then I would do 5 pi over 6, and the y value would be 2 again. And then I would do pi, and the y value would be back to 0 again. So these values would just be duplicates of the previous values. And there's my circle in polar form. So this would be 2 pi over 3. This would be 5 pi over 6. And then this would be pi. Okay. So this completes a circle in half of a rotation. So you only have to go from 0 to pi. In fact, you don't even need this last point. I don't know if you can see that last point. The point that you can't see here is the same as the top point. It's just back to 0, 0 again. Okay. So by the time you get to pi, you're already back to 0 again. So it does an entire circle. So if you went to 2 pi, if I were to continue to go around to 2 pi, it would just draw this circle again. So the period of this is 1 pi. All right, which is interesting because normally the period of a sine function is 2 pi. But it draws out this graph in a period of half of that, so 1 pi. Okay. So we could generalize this if we want to have a general form. In general, what's a general principle? R equals A sine theta is a circle. That is tangent to the x-axis. And so if A is greater than 0, then the circle looks like this. And this would be the point A. The center would be A over 2. Although notice in polar form, you don't even plot the center. Which is actually more realistic because, you know, in algebra, it kind of always bothered me that we make such a big deal about plotting the center. You know, in my intermediate algebra class, I make my students plot the center. But technically, the center is not part of the circle. Yeah, it's something we just kind of ignore throughout basic algebra. So if A is greater than 0, then the graph is above what we used to call the x-axis. It's now called the polar axis. You can still call it the x-axis if you want. No, everybody will know what you mean. But technically, you want to be the life of the party. Well, I beg to differ. It's called the polar axis. And if A is less than 0, then your graph sits below the polar axis, like this. Okay. And again, the center is half of whatever A is. And again, in polar form, this graph would just look like this. You know, it would just be underneath what we used to call the x-axis, but it's now called the polar axis. Okay, so that's pretty much it for circles. Next, we're going to graph, let's graph R equals 4 cosine 2 theta. Okay. Before I break out the graph paper, let's just go ahead and make a table of values that we can get going. So remember, theta kind of acts like x, and R depends on theta. It doesn't really matter what order you put the chart in. I like to put them in the same way that I did x and y in algebra. I also teach a lot of algebra, so I'm kind of a algebra machine. I don't even think about it anymore. I just do it. Fill these all out. So I pick my theta kind of like in algebra. I tell you to pick your x, plug in your theta, and then give me what the r is. If you try to pick r, it's much more difficult to solve this equation if you pick the r. Much easier to pick the theta. I'll leave that to you. And I usually tell my students all the same thing. If you don't know where to start, start with nothing. Yeah, you got nothing to do, but you got nothing to gain. Nothing to lose, sorry. Everything to gain. All right, so we're going to plug in theta equals 0. Cosine of 0 is clearly 1. So we're going to get 4. Now notice this is a double angle, but I don't recommend using any double angle formulas or anything like that. It's just keep your eye out on it. It's a double angle. So what that means is that when I plug in, say, pi over, I don't know, what should I plug in? Pi over, let's see, let me look at my graph paper. What do we got here? Say pi over 6. Yeah. Actually, I changed my mind. Let's do pi over 12. I had to really think about what I wanted to plug in. If I plug in pi over 6, I'm going to immediately double it, right? So I'm going to start with pi over 12, and then when I double it, watch what happens. I know in the last one I didn't really show the doubling. It's technically that's 2 times 0. I got away with it that one time. That's the only time you would get away with that. In the future, you make sure you double the angle. And again, you don't have to use any doubling formulas. You just literally multiply the angle by 2. Yeah, so you get 2 times pi over 12, which is pi over 6. That's what I was going for. I was going for pi over 6 because that's a special angle. But I notice I used pi over 12. So keep your eye out on the double to make your choices. All right, and sometimes you'll make some bad choices as long as you go back and fix them. So now I've got 4 times cosine pi over 6, which is radical 3 over 2. So I got 2 radical 3. You're going to notice these numbers are going to come up quite a bit. Radical 3 times 2 is 3.46 or 3.5. For all practical purposes, when you're doing it on your mouse, you can just do 3.5. Oh, there's an interesting way to graph these on the computer that I'll talk about later. It's almost too easy. You just kind of drag your mouse, and it's just going to draw the graph as you go along. All right, so let's go to pi over 6 now. So notice what happens when I plug in pi over 6. It's going to become pi over 3. So I got r equals 4 cosine 2 times pi over 6. That's going to become pi over 3. Yeah. You're multiplying it by 2. And you all know what cosine of pi over 3 is. It's 1/2, so that one's just going to become 2. All right. What else can we go to? Pi over 4. So r equals 4 cosine 2 times pi over 4. You are allowed to use any numbers you like, but make good choices. Choose numbers that you already know. If you don't already know these, then this is your chance to refresh yourself. Every time you pick a theta, see if you could quiz yourself mentally. You know, you got to kind of be your own boss right now. I'm not going to be around to tell you what to do. Cosine of pi over 2 is 0, so that goes back to being 0. All right. If you don't know how to make good choices about what to plug in, then just make lots of bad choices, and you'll just suffer a little more, you know. Eventually, you'll get it. I can't tell you how many bad choices I made before I finally got the hang of this. All right. Let's try a couple more. How about pi over 3? 4 cosine. Notice why I don't have the graph paper out yet. You're going to need a lot of points in order to break out your graph paper. So this is 4 cosine 2 pi over 3. Remember, cosine of 2 pi over 3 is negative 1/2. So So that's negative 2. All right, and then pi over 2. Notice there is sort of a pattern. Look at the denominator. 12, 6, 4, 3, 2. A little bit of a pattern. I wouldn't get too comfortable with that because then will then change in my next round. So pi over 2, what do I have? I have r equals 4 cosine 2 times pi over 2, which is 4 cosine pi, which is 4 times negative 1, which is negative 4. It looks like I skipped a number in here. Yeah, you see the pattern? 4, and then negative, and then 3.46, then 2, then 0, then negative 2. There's actually a negative 3.46 in between here. If I really wanted, I could go back and recover that. I guess it would be 5 pi over 12. See, I didn't think to make that choice. Right? But after I realized I missed that chance, I can still go back and pick it up. 5 pi over 12 would become 5 pi over 6, which would be negative root 3 over 2. And that would be negative 3.46. So that negative 3.46 would go down here, right in between here and here. It's only if you want symmetry. It's okay if you miss a point or two. Okay. Let's see what happens next. So after pi over 2, where should we go? We're going to need a lot of points for this one. It's because the double angle is causing us to have to pick a lot of points. So after pi over 2, where should we go? I don't know. How about... So you're on a circle. You got pi over 2 here. How about right here? It's a little bit more than pi over 2. How about 2 pi over 3? And I wouldn't really worry too much. If you get some weird numbers, you can always adjust them when we get out the graph paper, which is coming soon. So you got 2 pi over 3. So I got r is 4 cosine 2 times 2 pi over 3, which is 4 pi over 3. Cosine of 4 pi over 3. That's going to be negative a half again. So I'm back to negative 2 again. I'm probably not going to plot the 3.46 anyway. I mean, if I have to, I will, but you can kind of see you missed another one. Right? I'm not going back to get this one. I mean, every time you, in this example, every time you have a 4 and a 2, you're always going to have a 3.46 between it. Yeah, it's a periodic function. So if it hits it on the way up, it's going to hit it back on the way down, or vice versa. All right, let's finish this off. Let's pick just a couple more points, 2 more points. Let's do 3 pi over 4, and let's just get to pi and be done with it, okay? I think that'll be enough to finish this graph. So I got r equals 4 cosine 2 times 3 pi over 4, which is 4 cosine 3 pi over 2. 3 pi over 2 is, the cosine is 0, so this one's going to come out to be 0. 3 pi over 2 is down negative 90 degrees, or if you go this way, 270 degrees. So its cosine is 0. And finally, at pi, we have r equals 4 cosine 2, and then times pi. So that's 4 times 1, so that one's back to 4 again. I always want to make sure I'm back where I started, and then I can say that I'm done. All right. If you don't end up back where you started, then something went wrong. Well, maybe I shouldn't say done yet, but I think I'm actually half done. But at least I'm back where I started. All right. Well, we'll see how the graph turns out. All right. That's the fun part. Okay, so you've got all these points here. So you spend some time getting some good points. We'll plot the 3.46s. We'll plot them as 3.5 if necessary. You might want to remember what the function is. It's r equals 4 cosine double angle 2 theta. So we got some polar graph paper here. We're starting with 0 degrees. So it's 0 degrees right here, or 0 radians. And 4. So 1, 2, 3, 4. Each concentric circle is radius 1. So 1, 2, 3, 4. Now, I should mention, when you put them over here, it's technically like this, 4, 0, which is one of the dangers of writing them this way. The r comes first and then the theta. I know, I probably should have made my table the other way, but it doesn't matter. I'm not going to label every point anyway. You've got them all right here anyway. All right, pi over 12. Let's see, what are these divided into? This is 1, 2, 3, 4, 5, 6. So this is pi over 12. Yeah, right here. This angle right here is pi over 12. It's 15 degrees. Right there is pi over 12. Nice. So 3.46, so go out about 3.5, right about there. 3.5. All right, and then we're at pi over 6. So pi over 6 is right here. That's 30 degrees. So pi over 6 and 2. So 1, 2. All right, pi over 4, and radius is 0. That just puts you back at the pole. So anytime the radius is 0, you're back at the pole. All right, pi over 3. That's supposed to be a pi over 3 here. Got a little bit erased. And negative 2. So pi over 3 is right here. You might think I skipped pi over 4, but it's right here. Pi over 4 was the one that went all the way back to the pole. So it's like the radius shrunk down to nothing. Now we're at pi over 3. Pi over 3 is 60 degrees. Now radius is negative 2. So you go out to positive 2. Don't plot it yet. Reflect it across. Try to stay on the same line and come over here to 2. Did I hit it? Kind of hard to tell. Let's see. I don't think I did. I think I missed it. Oh, no. Good. I'm on the same line here. So it should be the same line as pi over 3, but reflected onto the other side. That just seems weird. It seems out of place. All right, let's keep moving. 5 pi over 12. 5 pi over 12 is right here. Oh, I see why. You'll see in a second when it finishes. So 5 pi over 12, we got negative 3.46. So that's about 3.5. So right about here. But you're going to go negative, so you're going to follow it all the way through. Negative 3.5, right about here. Okay. I wouldn't start connecting dots yet. I mean, you might think you see something, and that's not really what you see. So be careful. All right. I thought I saw something that I didn't see just a second ago, and I was about to panic. All right. All right, keep going. So I got pi over 2 and negative 4. Pi over 2 is easy. That's just 90 degrees, right? Pi over 2, 90 degrees. Negative radius 4, so you go up 4, but then you reflect it down here. There you go. I just realized this says 3.5, but I plotted it at 2.5. That's already a mistake. So this one is a mistake. We'll cross that one off. I didn't realize this says 3.46, and I accidentally put it at 2.46. So correct that point, put it right there. You can kind of see, look, the pattern here should be relatively predictable. It's kind of like watching the sun go up and the sun go down, or the phases of the moon or something. I mean, if you know what it was doing last night, you can kind of predict what's going to happen tonight, right? Okay, where are we at? I know, this is a long process. So now we're at 2 pi over 3 and negative 2. So I skipped one, so 2 pi over 3 is here. I skipped one of my pi over 12s. And then radius is negative 2, so we go out radius 2. And then we reflect across, stay on the line, and go right here. And you can kind of see the one we skipped. The one we skipped was right about here. It would be symmetric with the last one. You can kind of see the pattern here. Okay, and then we're going to go to 3 pi over 4 is next. That's right here. Oh, radius 0, so it just puts it back at the pole again. And then pi, oh, I skipped a whole bunch, didn't I? So I skipped all of these. We might want to fill those out later. And then pi comes out to be radius 4, so that puts me right here. Let's start to draw it now. Okay, and so now you can kind of see what happened. It's a periodic function, so it has to repeat these values again. Yeah. So the next one is just going to be back at 2 again, radius 2 again. I can make a table and keep filling it out, but it's going to follow the same pattern. And then it's going to go to 3.5 again, right about there. Okay. And then it's going to go back to 3.5 again, and then back to 2 again. And then back to 0. So this pattern, 4, 2, 4, 3.5, 2, 0, negative 2, negative 3.5, negative 4. In between these two, there was another negative 3.5, 2, 0, 4, right? So there was another 2 and then another 3.5. It's just going to keep doing that pattern over and over and over again. And then it's going to come up here. I could come over here and make a whole nother list of points, but it's just going to accumulate the same points again. Repeat the same points again. You're going to get 2. You're going to get 3.5 again. You're going to get back to 4, back to 3.5, back to 2. And then down here, it's going to go back to 2 again, and then back to 3.5 again. And it's going to complete the entire, what's called a 4-petal rose. I know it doesn't look much like a rose, but it's a flower, and so it got dubbed the 4-petal rose. I should mention that the 4 petals does not come from the number 4 here. So that's a coincidence. The 4-petal rose comes from the 2 theta, is what made it a 4-petal rose. So it's not this 4 that matters. It's the 2 that matters. And so in general, a 4-petal rose of radius A is R equals A cosine 2 theta. Okay. So what makes it a 4-petal rose is that it has a 2 theta. So 2 times 2 is 4. All right. I really probably should have done, I like to think I did it intentionally, but I should have done, R equals, 5 cosine 2 theta. The reason why I didn't is look at my graph paper that I printed out. It only goes out to 4, and I wanted to fill up the whole thing. So if I didn't have that piece of graph paper and I was using 5 cosine theta, then I go 1, 2, 3, 4, 5, and then I would still have the same 4-petal rose like that. And then this would be 5, and then this would be 5. I know I drew it badly. And then over here, and so on and so forth. If you use the polar paper, it comes out a lot nicer. So the 5 is telling you what the radius of the rose petals are. How long is each rose petal. I wish I could tell you that there was a nice pattern for the number of leaves, but it's really all over the place. You kind of just have to look it up. So that's a 4-petal rose. A 3-petal rose has a 3 in it. Yeah, it's A cosine 3 theta. And it kind of looks like this. Although I drew that very badly. God, it's still terrible. I need to just use the polar paper. But I don't want to make you sit through another half an hour long graphing pattern. So this would be a 3-petal rose. It should look a lot nicer. Looks better if we use polar paper. But just to give you the idea of what a 3-petal rose should look like, I keep wanting to make it look better. And then again, A is just the radius of the petals, how large each petal is. I'm not going to give up on this, am I? There you go. That's a 3-petal rose. There is a general pattern. So if it's odd, then this is exactly the number of petals. So for example, A cosine 5 theta would be 5 petals. Etc., etc., etc. So if the multiple of theta is odd, then that tells you exactly the number of petals. 3, 5. If I wanted to do 7 petals, it would be A cosine 7 theta, so on and so forth. However, if even, so R equals A cosine 2 theta, or R equals A cosine 4 theta, or R equals A cosine 6 theta, then it's double. So 2 would become 4 petals. 4 would become 8 petals. And 6 would be 12 petals. And, and I could post a whole nother hour-long video of me sitting there plotting every single point, and you would realize that it has to do with the periodicity of the function. If this is even, it takes twice as long to finish its cycle, kind of like this one here. Yeah, I would have had to go around this graph 2 full rotations in order to draw all 4 petals. I don't know if you noticed, but we did half a rotation and we only got a portion of this graph. I think we didn't even get 2 full petals. We got 1.5 petals. So you have to go around quite a bit to get the entire thing. If the multiple is odd, you have less rotations in order to get all of the petals. And so maybe I'll do an example in a minute before I finish this video, but I'm coming up on over an hour now, so I want to move on. Okay, this is probably the last example we'll have time for today. So this is a 6 minus 6 sine theta. I'm going to do the same thing I did last time. We're going to make a whole bunch of points before I break out the polar graph paper. I always recommend starting with 0. For theta. We could try to do some of these with mental math. It probably would speed things up quite a bit. I'm only going to use angles that we know by heart, so we should be able to do this pretty quickly. I will use a calculator if necessary. So sine of 0. Well, sine of 0 is 0. Yeah. So 6 times 0 is 0. 6 minus 0 is 6. All right. Now we'll go to 30 degrees. Pi over 6. All right. I don't have any double angles here, so I'm not worried about picking weird pi over 12s and things like that. So I got sine theta, pi over 6. Sine of pi over 6 is 1/2. 1/2 times 6 is 3. 6 minus 3 is 3. We can go to pi over 4. All right, sine of pi over 4 is root 2 over 2. Okay, root 2 over 2 times 6 would be 4.24. And then 6 minus that would be 1.75 or 1.76 technically. Okay. And again, if you have to, do what I did last time. Make a big mess out of it and plug everything in and work it all out. I'm trying to exercise some mental math powers here. Pi over 3. Sine of pi over 3 is root 3 over 2. So root 3 over 2 times 6. Actually, I'm doing a trick here. Root 3 over 2 times 6 is the same as root 3 times 3. Yeah, because you can cancel a pair of 2's. And then minus 6 minus that gives you 0.8. Pretty much exactly 0.8. 0.803, so 0.8. Pi over 2, sine of pi over 2 is 1. 6 times 1 is 6. 6 minus 6 is 0. It's a lot more efficient than all that messy stuff I was doing earlier. If you've got a really good calculator, you can actually, some of the more fancier ones, I don't have one, you can type in the formula and then just do various values of theta. Literally set up a little factory on your calculator, just cranks out all the R values very quickly. All right, notice what's going to happen. 2 pi over 3. 2 pi over 3 is going to be the same as pi over 3 because they have the same sign. Yeah. So sine of 2 pi over 3 and sine of pi over 3 are both the same. So that's just going to be 0.8 again. Okay. Maybe I'll finish over here if I've got some room. Do I have room? I've run out of board down here. So after 2 pi over 3, we'll do 3 pi over 4. Again, 3 pi over 4 will be the same as pi over 4. So use what you know about the unit circle and about the trig function in hand, which in this case is sine, and make sure you know that it has a symmetry to it. The sine of 3 pi over 4 is the same as the sine of pi over 4. So you don't have to do that all over again. And then 5 pi over 6, what's going to be the same as pi over 6? So these numbers are just going to happen in reverse. And then when you get to pi, you're going to be back to 6 again. So these are going to be all the ones in which the radius comes out positive, excuse me. Now we're going to move past pi, so now we're down in the lower quadrants. We're down in quadrants 3 and 4 in the below. So we're going to get negative signs. Yeah. So let's go 7 pi over 6. 7 pi over 6. Well, that's the same as pi over 6. Let's work it out, though. It's going to be negative, right? So it'd be negative 1/2. I'm actually going to write this one down. So that one's not going to repeat a value again. It's going to go to 9. Because you got negative 1/2 for the sine. And watch, you're going to see a similar type of pattern. It's just going to grow. It's going to get larger because you're going to have this negative thing here. Okay, what's next? 5 pi over 4. 5 pi over 4. So what's the sign of that? Negative root 2 over 2. So negative is going to turn into a positive. The 2 is going to cancel, make that a 3. Root 2 times 3 plus 6, 10 1/4. 10.24. What else do we have? 5 pi over 3, 4 pi over 3, 4 pi over 3. Remember, sine of 4 pi over 3 is just negative root 3 over 2. It's the same as one of these previous signs, but it's negative. Now I have to be careful. So that's going to be 6 plus 3 root 3. So that's going to be 11.2. 11.196. So 11.2 basically. All right, and then I think I only have room for one more, and we'll have to start graphing 3 pi over 2. So 6 minus 6. Sine of 3 pi over 2 is negative 1. That's going to be our largest R value, which will be 12. I don't have a big enough piece of polar paper to go all the way to 12. So we'll have to do some clever adjusting of our scale so that I can get to 12. Okay. So let's see. 1, 2, 3, 4, 5, 6. We're gonna count by twos. So we're going to call this, so each circle is 2 units. All right. That'll be our scale. So each circle has a radius of 2 units. Okay. Otherwise, I'm never going to be able to make it to 12. All right. So 0, 6, 0 degrees and 6. 1, 2, 3. So I'm counting by 2. So that's going to be 6. If I start putting numbers on this, it'll be so messy you'll never be able to read the graph when it's done. All right, pi over 6 and 3. Oh, no, I don't have any pi over 6s here. Yeah, I do. This is pi over 6. Nice. This is pi over 3. I might have to skip some of these other ones. This is pi over 2, so I keep track of this. So pi over 6 and 3, right about here. All right, pi over 4 and 1.76. Ooh, pi over 4 would be kind of in here. Right in the middle of pi over 6 and pi over 3 is pi over 4. And 1.76, I might as well not even plot it, but I'll try to be right about there. You can barely see it because of my scale. I'm probably just going to avoid all of these guys in the future. They're too hard to see. All right. Pi over 3 and 0.8. Pi over 3 and 0.8. Oh, if I can't see 1.7, I definitely can't see 0.8. 0.8 is so close to the origin. It's like that. Pi over 2 and 0. That is the origin, or the pole, as we call it in this setting. 2 pi over 3 and 0.8. So 2 pi over 3 is over here. God, I wish I didn't have that 12. I think this would be a great piece of paper if you could see everything. And then it's going to be 0.8 again. So it's, again, right here. It's going to be very difficult to see. And then 3 pi over 4 is right about here. Halfway between these guys. And that's going to be right about there. Again, those decimals are very difficult to see. Let's go to the next nice one. 5 pi over 6 would be right here. And the radius is 3, so right about there. All right, pi and then 6. So pi is over here. I'm counting 2, 4, 6. So each circle is 2 units. 7 pi over 6 and 9. 7 pi over 6 and 9. So 2, 4, 6, 8, 9 is halfway between 8 and 10. 5 pi over 4 and a little bit more than 10. So 5 pi over 4 is here. 2, 4, 6, 8, 10. So just right about there, a little bit more than 10. 4 pi over 3 and 11. Well, if that's 10, then this is about 11. Yeah. And then 3 pi over 2 and 12. Again, I'm counting by 2, so 2, 4, 6, 8, 10, 12. I could have kept going. You're going to see a pattern. It's going to be very similar. The 4 pi over 3 is just going to duplicate on the other quadrants. These points are going to have the same radius. I mean, it's going to continue this pattern. And then when you get to the next one, it's going to be here again. And then here again. So everybody has sort of a partner on the other side of the fence. And there's your graph. It kind of looks like a heart. So it's sort of heart-shaped. And so we have a name for this. It's called a cardioid. Make sure I spell it right. Yeah, it's got double I's. O-I-O-I. So this shape is called a cardioid. Yeah. You might recognize the name from your science classes, cardioid, heart. Yeah. A heart doctor is also called a cardiologist. Yeah. So this graph is called a cardioid. There are various types of cardioids. The general form is A plus or minus B sine theta. That would either be a cardioid that faces up, kind of like the one we just did, yeah. Or sometimes the cardioid ends up facing the other way, like this, upside down, depending on the values of A and B. So whatever these values of A and B are. I don't want to give away too much. I'd like you to play around with it. In this case, A and B are equal to each other in this case, and B is negative, obviously. So we have this case. I will tell you that there are other orientations of this. For the sideways cardioids, they kind of point like that, or sometimes they point like this. Yeah. And this would be the A plus or minus B cosine theta. So if the cardioid has cosine, then it's going to face left or right, again, depending on A or B. Okay. And it's going to be up or down, again, depending on A and B. The cardioids are part of a larger family that are called the limacons. Limacon is French for snail. And so we have different types of cardioids that sometimes have a loop inside of them. I don't know, some Frenchman in the 19th century was eating his escargot. Has anybody ever eaten a snail? When you take it out of its shell and you look at the actual part that you eat, it sort of looks like this. It's got this weird little thing. It's the foot of the snail, and then there's the meat of the snail. And so when you pull it out and you're using your little escargot spoon or spork, the French had actually invented the spork. It was used for escargot. It's a little half spoon, half fork. And you pop it out of the shell, and it sort of resembles this. If A is less than B, then you get a loop. The same formula that we just talked about, the A, B, cosine theta, sine theta. Okay, this lecture's gone on long enough. I'm going to get it up there as soon as possible. I'm not going to spend a lot more time on the graphing. I want you to play around with it a little bit and give me your feedback. Let me know if there's anything you have trouble with. I did leave a few loose ends out there for you guys to tie up on your own. This section is really meant to be exploratory. I want you to get in there and actually start drawing some of these graphs. The computer does not have a very good application for drawing these, so I want to apologize in advance. You're basically going to use your mouse and you're going to draw the picture. So when you're graphing online, complete one full cycle of the graph. Once the graph is complete, stop, and then that should mark it correct. If you overdo it, or if you stop shy of completing the whole graph, suppose you only draw that much of the graph, you're not done yet. So you want to, on canvas, slide the value of A so that, I don't know why they use the letter A. I really should have changed it to something else, like theta or something like that. Maybe I will. Maybe I will change that to theta if I can, so that the graph is complete. I'm not even going to see if you can see the word complete there. Again, you're going to sort of draw the graph by sliding. There's a little slider bar here where you slide A. A is sort of acting like theta. It's acting like the angle. I think the computer uses the letter A to represent angle. I never do that. I use A as a constant. So you're going to slide the A in such a way that it draws the entire graph, like that. Or like that, or whatever the case may be, okay? This is supposed to be playing around. It's not supposed to be complicated or stressful. So if you're stressed out about it, let me know, and I'll sort of walk you through it step by step. Okay, unfortunately, we're not together in the classroom. I really had a great lesson planned for you guys. I was going to pass out. Everybody was going to get a packet of these graph papers, and we were going to have a polar fun graph day today. But it's just not happening. We're having it from our kitchens and our bedrooms and such. So, Dr. Jordan signing out. Until then, see you on the internet.